video, we'll talk about how we can model the body effect of MOSFETs into the small signal model. Okay, how we can include its effect into the AC equivalent circuit models. Now, if you recall, we have already talked about the body effects in part 10 of the lecture series. So what it means is that now this, okay, what happens in actual MOSFETs or IC devices. Now you see over here, for example, you have two NMOS devices, M1 and M2. Okay, and because it's an NMOS device, so the channel that you're going to establish is by applying the gate voltage at least greater than the threshold voltage of both devices VTN1, and then we are going to have this another gate voltage, let's call this VG2 greater than VTN, which is already shorted with the VDD, so it has to be greater than the threshold voltage anyways. Okay, so we have two devices, M2 and M1. Now, uh, this voltage is required to establish a channel, okay, in both devices. So what happens is that normally the source terminal of NMOS device is grounded, okay, and it's at the same signal ground as the body is, okay. So the body, the bulk of the or the semiconductor material of this MOSFET device is at the same ground potential as your sources. Okay. Well, now what happens is that once you can have more than two NMOS devices on a single IC. So, for example, over here, the drain D1 and the source S2, they share a common terminal V0. Okay. So if you have turn on the device, so if you have turn on M1, you have to apply a certain VDS over here, okay, and that VDS will the effect will be to apply a horizontal electric field. So once the channel is established such that the gate voltage is greater than VTN, so you have the channel, so the n-type charges or electrons, they start flowing from source to drain. Uh, this source S2 is no longer at the ground potential. Okay, this will be at the same potential as the VDS1. So VDS1 is not at 0 right now. Okay, so therefore, I mean the VD1 is not at the ground potential, which means VD1 is the same as VS2. Okay, so this is not equal to 0 anymore, or this terminal is not at the same potential as the body is. So what happened as a result is this is positive, this is negative doped region. Therefore, there is a p-n junction which forms over here, and as you apply the VDA, the potential at the drain terminal, which is the same at the source S2 of MOSFET M2, the depletion width increases. Okay, the depletion width is going to increase, and as you increase the field, the depletion width increases more. This results, although there is a reverse biasing over here as well, because both the NMOS devices have their n-doped source regions and drain regions. So already there is a reverse biasing over here, okay, because this is n-doped and this is a p-type substrate. But over here the depletion width is more due to the positive electric field that is being applied at this drain D1 and S2. So due to this uneven depletion width compared to what you have over here, you'll have a channel, something, the physical channel will be tapering off like this and like this in both regions. Okay, so basically the point where the space charge density is 0, it might shift towards right and towards left in these regions, okay, depending on how much VDS you are applying. So basically you are physically what you are doing is you are changing the length of the channel. Okay, the length of the channel physically is changing with regards to VD1 over here, which is equal to VS2. Okay, so VD1 is VS2. So the point is that no more the source S2 is at the ground potential. Okay, although S1 is at the ground potential, but S2 is not at the ground potential. So that means with respect to the bulk or with respect to the common P substrate, there's a reverse biasing over here, which will change the channel width, and in turn it will change the threshold voltage requirement, therefore affecting the overall device performance. Okay, so what happens is that your threshold voltage due to the source and bulk voltage or the reverse biasing that exists, the threshold voltage changes. Okay, you see here if your VSB is 0 in this expression, if VSB, I mean the bulk and the source, if they are at the same potential, if they are the same potential, then this expression reduces to VTN. Okay, I mean this expression is okay. This is VTN, is it becomes VTNO. Okay, but this factor is non-zero due to the reverse biasing of source and bulk regions. Okay, now phi of f is the semiconductor doping concentration parameter. Okay, typically it's of 0.35 volts. Gamma is the body effect parameter. Okay, but again, this whole term is insignificant if your source and the bulk are at the same potential and they are at the same ground. So normally in this symbol of MOSFET devices, we don't show this bulk terminal. Okay, we consider the MOSFET to be a three-terminal device with drain, gate, and source. But over here, since bulk is P-type, and this shows P to N, the arrow is the direction of P to N. So both devices are NMOS devices. In figure A, you're looking at the DC quantities, capital V, capital GS, okay, capital case letters I and V. So voltage and currents are DC quantities in part A. So this is NMOS enhancement device with the DC voltages, okay. And in part B, you have AC voltages, small signal quantities that are being shown over here. But there is a finite bulk to source potential difference that is existing. Due to this, and since you know that for a linear amplifier, you're going to have a small signal or a low frequency component, AC component with the gate, which in turn is going to introduce a small signal AC component in the source to bulk, which is going to create, besides the DC component, a small signal AC component given by VBS, okay, over here. And this is going to change the threshold voltage. This is going to change the threshold voltage. So the body effect that occurs in MOSFET, in which the substrate or the body is not directly connected to the sub source. So for an NMOS device, the body is connected to the most negative potential in the circuit, and it will be the single ground. But figure 12A shows the 4-terminal MOSFET with DC voltages, and 12B shows device with AC voltages. So keep in mind that VSB must be greater than or equal to 0. So the simplified current voltage relationship, once you know, if you, I mean, for the transistor to operate in a linear or to operate as, so for the MOSFET to operate as a linear amplifier, it has to be biased in the saturation region. Okay, so this is the saturation current, which has the threshold voltage. But what happens with this body effect is that VTN is going to change. VTN is going to change with respect to the source and bulk VSB voltage that exists, because this exists because there is a reverse biasing which is happening between the bulk and the source regions. Okay, so there exists a finite VSB which is greater than 0. Okay, this VSB greater than 0 affects your threshold voltage. Okay, so if the threshold, if VSB decreases, the threshold voltage decreases. Okay, if threshold voltage decreases, the current ID increases. Okay, the current ID increases because VTN is decreasing. So you see these effects are interrelated. The threshold voltage changes due to the body effect, and this is due to the reverse biasing of the body and the source. The body and source are at different potentials. If they are the same potential, your VSB is 0. Okay, and in that case, there is no problem. Okay, you can go ahead and use the same. You can use the same relationship. Okay. So you can use the same relationship for the saturation current over here. Okay. So to model this effect, let's consider the back gate transconductance parameter, as we have done for the transconductance parameter of the MOSFET device. So now the thing is, now if an AC component exists in the source to body voltage VSB, there will be an AC component induced in the threshold voltage. Okay, so which causes an AC component in the drain current in return. So if there's an AC component, in the source and bulk voltage, okay, if there's in the reverse biasing, if there's an AC component over here, then there will be an AC component in the threshold voltage as well, okay, which is going to affect your drain current. So so what we're going to do is to model this effect into the small, or to include this effect in the small signal model, we find a back gate transconductance parameter given by GMP. Now this is given by partial ID over VBS because we understand that the current is dependent on threshold voltage, which is in turn depends on VBS. Okay, so partial, if you take the derivative of ID with respect to VSB, we call this at the Q point, we call this the backgate transconductance parameter. So what it is, you can write this as partial ID over VSB with a negative sign. Okay, this is BS, so this is SB. This can be written by the chain rule if you take the partial derivative with respect to the threshold voltage, and then you can write this as partial threshold voltage divided by SB, because VTN is depending on so you can find what VTN is depending on SB, so you can find the dependence or the gradient of this curve of threshold voltage with respect to VSB. Okay, so we can find this and plug this into this over here in the chain rule to find the backgate conductance. So from the equation of the saturation current with regards to VTN, the variation with regard to VTN in the drain current, we have this GMB as minus 2Kn VGS VTN, and we call this as minus GM. Okay, so it's very similar to the transconductance parameter GM. So the only difference is the minus sign over here that is coming up. So this minus sign shows up over here as well. Then from the equation of VTN, which is also depending on VSB, so this expression is going to be, this is partial ID with respect to VTN, the variation of the drain current with respect to the threshold voltage. So this is the first part, and then we have this the threshold voltage, which is varying with respect to the source and the bulk or the body of the MOSFET. This is going to be plugged over here, and if you take the derivatives with respect to SB over here, so if you take the derivative of this expression with respect to SB, you find this, the first term, it does not contains any VSB, so the first term is 0. Third term is also 0, so it's only the second term. Okay, so it's like this. This parameter is called eta. Okay, so what you have is the back conductance, gate conductance parameter becomes equal to minus GM into eta. Okay, again, you see the transconductance nature of this body effect is that for the given AC component of okay, this is eta. Let me write this down first. So this becomes GM. The backgate conductance is your GM, which is the transconductance parameter of the MOSFET, multiplied by eta, and eta is given as such in terms of the body parameter gamma. Okay, and the doping function phi. So okay, now you see we have we how we evaluate this is the interpretation of the backgate conductance is that it's again a transconductance parameter, which means due to the AC component in the source and bulk, you have that effect in the current. Okay, so the AC component VBS multiplied by the backgate conductance parameter GMB, input is again the due to the, or the input you might say due to the bulk source potential difference, you have the effect on the drain current. The output effect happens on the drain current. So the drain current component, AC component, is due to the body effect. Okay, that's how you model this, due to the body effect. The other effect that you need to consider is due to the input voltage at the gate, and that is simply VGS. Okay, so you have an AC component at the gate, VGS, that is ID. That is also another component called, let's call this ID2, and let's call this ID1. So ID1 plus ID2 is your total drain current. So ID2 is due to the input AC gate voltage at the gate. Okay, then ID1 is due to the body effect due to the AC bulk to source voltage. So if you add them up, you will have these two currents. They'll add up. So you will have two dependent sources in your small signal model. So one is there to for, so over here you see this is the small signal equivalent circuit of NMOS device, including the body effect. Now this is backgate conductance. Okay, and because the current has a dependence on VBS, so this dependent source generates the current which is dependent on the bulk to source AC component. Okay, there is a potential difference, and then there is a AC component between the bulk and the source terminal. regions. So you have this dependent current because of the bulk source body effect, okay, and then you have another dependent source due to the gate source applied voltage, okay. So these two currents are going to add up, and then you have the forward resistance of the actual MOSFET, and VDS is the output voltage, okay. And we don't have any input, again we don't have any input resistance. Why? Because we are considering a low frequency signal, so the gate capacitance can be ignored. It's an open circuit conditions, okay. But again, over here you see there is a fourth terminal. There is, so three terminals are over here, gate, source, and drain. And this is the fourth terminal bulk, because the body is at a difference, has a different potential with respect to regard to the source. The potential difference exists, so VBS exists. Therefore, the threshold voltage is changing. The threshold voltage is changing because of VSB. If VSB was to be zero, then you don't have to model this effect into the drain current, okay? Because of VSB, VDN is changing, and because of VDN, there is effect on ID. So that's how you are going to model this. And since the input is VSB, so you are going to include this effect over here, okay? And then you have a back gate conductance parameter. So you have there are two dependent current sources, which which are to be included in the small signal equivalent model of MOS device. So the backgate conductance is then GMB GM, which is equal to GM into eta. This is GM. Okay. So including the body effect, the small signal equivalent circuit model is shown in figure 13. This is over here. So we note that the direction of the current and the polarity of small signal body to source voltage for VB is greater than 0 is given as such. Okay, it's just like for same for the NMOS device. It's the same as you have the direction for, even due to this bulk source potential, a non-zero bulk source AC component, if it exists, then the direction is the same, that the current that is generated due to the bulk source, the direction of the current, that current is the same as that generated by the VGS, the input voltage at the gate terminal, okay. So then VSB decreases, okay, since VBS is increasing, which means VBS increasing means VSB is decreasing, okay. So decrease in VSB means your VTN decreases, which in turn, since VTN decreases, your ID increases. So everything is related over here. So VTN decreases and ID increases. So the current direction and the voltage polarities are thus consistent. Now, this phi of f, which is a semiconductor doping function, is about 0.35 volts. Gamma is 0.35 volt under root, and the value of eta becomes 0.23. So you see the variation of eta when you have VSB equal to 0, and due to the semiconductor doping function, which is consistent, and that's about 0.35 volts. The body effect is 0.3500 volts. This parameter is going to vary from 0 to 23% of your transconductance parameter of MOSFET. Okay, so it's about maximum is about 23% variation. So this current you can say is 23% if VBS and VGS are the same, if they are small signal voltages. Okay, it might be different, but GMB is about 23% of GMS. So the value of VBS will depend on the particular circuit again, but in general, we're going to neglect the back conductance parameter of MOSFET due to the body effect. GMB is due to the body effect, transconductance parameter. We're going to neglect this in our design analysis, keep it simple. So in general, we are not going to include this dependent current source into the model. We are good with the NMOS or the PMOS device that we have developed earlier. So the only transconductance gain that we are going to consider that is going to generate the current is with regards to the VGS, that is the input voltage at the gate only. Okay, and then we have the output resistance R0. That's all.